Good morning, everybody. Before I introduce today's speaker, an announcement for next week, actually two announcements for next week. Wednesday's seminar next week will be on 2 o'clock instead of 10 o'clock due to Langutsky Day in the morning. The speaker will be Shachar Shani Kadmiel, and he'll be talking about seismology, earthquakes. You can see that. I'll send the title later on. In the Geological Survey on Sunday at 12, Yair will give a special seminar. And for today's speaker, we have Yair Cohen. Yair was a student in this department with Natan and did a short postdoc in Tel Aviv University, and now is a postdoc in Caltech working with Tapio Schneider. And he'll be talking about gradient non-balance, a new approach for tropical cyclone outflow. Thank you.
And here tomorrow, seminar here tomorrow.
Also tomorrow at the Cal seminar.
Hi, thank you. Okay, thank you very much, Hagit. It's really great to be home. So I was thinking what to talk about before I came, and nobody here actually heard about this work, but after my PhD was not, and I did 1 year in Tel Aviv University with Nili Harnik and Yair, and working on something I found really interesting in hurricanes that was also recently published, so I thought it might be more suitable, so she already read the title. It's a work that I started with Nili Harnik and Yair in Tel Aviv, and after a conference developed to be a collaboration with Dave Nolan from Rasmus in Miami, and King Zhang and his postdoc Dan Downtown from Penn State, and only recently with the new results I will show that are not published yet, with Steve Durden from JPL, where I was sitting last year until they kicked all the Israeli out and moved into Caltech, that works on hurricane observations. So I'll start with a bit of a very brief outline. We'll talk about gradient balance and hurricanes, and why is it so frequent, why is it important. I will give some motivation. Okay. And then I will talk about gradient non-balance, which is a completely new approach to the outflow of hurricanes, and why do I think it's important. We'll show it in simulated hurricanes, in observations, and conclude. So a bit of motivation. I think this year can remind all of us why it's so important to understand hurricanes better. This is an actual part from a report of the National Hurricane Center in the US, where they do the forecasting of hurricanes and issue the warning for civils. And this is from hurricane, or at the time, Tropical Depression Harvey, the recent Harvey that hit Houston really badly. So it's on 10 p.m. in August 23. And what you see here is like what they describe they see on that day. So a report from Hurricane Hunter aircraft, which are airplanes that fly to the hurricane to take measurements, suggests that Harvey structure is consolidated a little bit. However, there have been no reliable report of wind indicating that the cyclone had reached tropical storm strength. It's not even hurricane, a tropical storm strength. 12 hours later, okay? And that's overnight. They wake up in the morning, and the issue is Tropical Storm Harvey, with Harvey now strengthening at a faster rate than indicated in previous advisors. The intensity forecast has become quite concerning. 24 hours later, you know how it ended, okay? We all heard the news, and the whole city was flooded. And this phenomena of hurricanes, it's Houston, yeah. You know the place, okay. Not like this, I hope. And this phenomena of hurricanes changing their intensity really quickly, what they call rapid intensification in the period of 24 hours, is still poorly understood. And in the forecasting of hurricanes, the mantra that everybody would say is that in the last decades, improvements in the forecasting of the trajectory of hurricanes have been really impressive, while the improvements in the intensity of hurricanes have been shameful. Okay, and everybody feel like we have to do something about it. In Miami, due to Hurricane Irma, they came up with this idea. It's a Facebook event to shoot the hurricane. It's very American. They like to bear arms. And then, according to Facebook, 30,000 people attended. I hope they didn't, but if they are, I'm not sure how many returned. Eventually, the police had to stop this event because it became really viral in Miami. And so I would give a brief kind of Hurricane 101. This is literally a figure from Wikipedia to describe a little bit about how we see hurricanes, what do we know about them. Then I would say what is our new output and how it fits to the general picture or how it modified it. So the Wikipedia image shows most of it. What we know about hurricane is a very strong, what we call primary circulation, horizontal circulation, which is very strong near the surface. Hurricane speed winds at the top of the atmosphere are not very rare, or he can tell you studying for his PhD and even later Hadley circulation. If the Hadley circulation had maximum winds near the surface, we would be in a whole other problem. Hurricanes wouldn't even interest us. But what's special about hurricanes is their ability to create this really strong wind near the surface, where it's really abnormal. And this has to be sustained by a lot of energy production, because near the surface you have friction that dissipates the wind all the time. This energy production comes from a secondary circulation, which is this in, up, and out motion that carries the moisture collected at the surface, translated into latent heat at the center, and then this heat is converted into pressure differences and kinetic energy. And this motion is flaring outwards, so the air that starts here at the top of the boundary layer is projected outwards in a curved motion or a slantwise motion. You can understand it from angular momentum conservation. So this is the total angular momentum of the flow. It's the relative plus the planetary one. If you start at one point, and at the second point you have the same angular momentum, the wind will be weaker because the pressure gradients are less strong than if the wind V prime here is weaker, but M is the same, R has to be larger, so you actually flare out due to conservation of angular momentum. And this is basically gives a general feature of a hurricane. Another way to think about it is energetically like a bank account. If you think about a hurricane as a bank account, you have revenue of energy from heat fluxes at the surface. So you have input of energy in the form of landed heat, of moisture and evaporation. And this is proportional to the velocity in the power of 1, absolute value of the velocity. And you have energy expenses. You lose energy at the surface due to friction, and the energy equation is proportional to V cubed. And so if you plot on a hypothetical velocity axis these two expressions, you see that you have a linear slope, a linear line and a cubic line, and they meet at 2 points. One point is where V equals 0, okay? So the energy production and the energy loss meet. So you don't gain money, you don't lose money in your bank account. And that is an unstable point, because if you would increase the velocity, the linear slope of the fluxes, the input, will be higher than the loss, and so you would propagate. The second point is a stable point, because at that point, if you increase the velocity, you lose energy due to dissipation, power of 3, more than you gain energy due to surface fluxes, so you would return here. If you would reduce the velocity, you would gain energy from the surface more than you lose it, and you will return. This point is basically the intensity of the hurricane. Okay? Of course, in order to really know it, you need to really solve this hypothetical velocity field. So you need to solve the dynamics. You cannot fully understand the intensity of the hurricane only based on thermodynamics, but you understand this point exists somewhere. The way to solve it, at least in our understanding, of course in weather models it's much more of a complicated system, but in our understandings, the way we understand it is based on a model that exists with us basically מאז קום המדינה, since the establishment of Israel, for a long time now. From Ernest Eliassen, it's like one of the most known meteorologists of the middle 20th century, and Jules Charny joined him later to work on hurricanes. So these are big names. And this model that explains the dynamics of the hurricanes is best as follows. You assume that up in the atmosphere somewhere there are no pressure gradients. And my talk would be actually on this. What happens here? Is it true to assume there are no pressure gradients? And therefore, if there is a warm core to the hurricane at the center due to convection, then the isobaric lower levels have to have a lower pressure at the center, because the temperature is the distance between these two lines. So it's a bigger distance here than here. If you do have a lower pressure, you would have circulation, you would have what we call a gradient wind balance here. And that wind would generate surface fluxes, so you can see it here by this cycle. The surface fluxes, due to convection, would convert the moisture here to heat here. And this would in return to a warm core, the surface low, and so on. And this is how you maintain a hurricane. Okay? So this is the model that base all of our understanding until today papers in 2015 and 2000 are still published, where they would solve a hurricane in a high-resolution model on the one hand, that doesn't assume explicitly all these assumptions, but then interpret the results based on our understanding on this model. So I would like to deal with this model the way we understand hurricanes. And the main point I'm trying to add something into this cycle would be, in this arrow here, how you convert a warm core to a surface low. Okay? Whether it's true to assume no gradients here and just project it downward, we have a more complex connection. So one thing I would like to talk about is this gradient wind balance and why it's so important in hurricanes. One of the reasons to assume gradient wind balance so strictly everywhere in the hurricane is because without a gradient balance, hurricanes wouldn't even exist. Okay, and that's what I'm going to show in the next two slides. So this is the geostrophic balance that we all know much better. It's just a balance between the Coriolis force and the pressure. And this is the deformation radius, and the two are tightly coupled. The deformation radius is the scale of Earth upon which you feel Earth's rotation, and you can actually obtain this balance. Now, atmospheric dynamics, in a way, I see that Alison or is Mark, I don't know, but they're not here. But atmospheric dynamics, in a way, splits into two. You have the large-scale flow people that study anything larger than the formation radius when balance exists, and the dynamics is deterministic by definition. The number of equations and the number of variables are the same. And you have people studying flows below the deformation radius, where the number of variables is larger than the number of equations. This is what we call three-dimensional turbulence, and essentially it is non-deterministic, and all you can do is a probabilistic approach. Oyama in '62 tried to explain how hurricanes exist and form based on this realization. So if I plot an hypothetical kind of cartoon plot of the radius of deformation on the y-axis in kilometers and horizontal scales of different phenomena in the x-axis, and this is the one-to-one line, anything on this side of the line is an atmospheric phenomena in which the horizontal scale is larger than the deformation radius. It belongs to 2D flow, predictable, deterministic dynamics. And any phenomena that its scale is smaller than the deformation radius would be here is a three-dimensional turbulence, and we cannot hope to actually make a deterministic prediction. We cannot only talk about probability. And if you add the values of the deformation radius to different places of the Earth, because it's inverse proportional to f, it increases towards the equator. So in mid-latitude you get 700 kilometers, in the tropics is 1,000 at least or more. And then you can put some phenomena on that we know, like hurricanes, mid-latitude cyclone, anti-cell, for example. And you see that while hurricanes reside here in the three-dimensional turbulence, mid-latitude cyclones and the Hadi circulations are actually on the other side. They're essentially deterministic. But hurricanes do have a component in them that is deterministic, and somehow they're able to cross from here down into here to be on the other side. And the way they do it is by replacing this balance, the geostrophic balance, in the gradient wind balance. So that's actually that motion. When you have a local rotation of the flow, so this is the centrifugal force I'm adding here. When you have a local rotation of the flow, you can locally reduce the deformation radius to the size of the phenomena and become deterministic in a turbulent environment. It's a magical process, and in the deformation radius expression, it comes about by adding this term, the local vorticity of the flow. So even though Earth's rotation is small and the deformation radius is large, you locally rotate the flow to organize, and after I've brainwashed you with this, I will show a video, which I hope will work. So this is from a Chinese satellite, Yair, in the Pacific, and what you're seeing is just clouds popping out in the atmosphere, and the time is moving fast. Every minute here is an hour. Maybe I'll turn one more light off. And it seems very chaotic in general, but what you would see is how it starts to organize in a very almost magical way. Here you can see that there are a bit of explosions in the center. And as it starts to organize at the center, convection outside will clear out, which indicates that it sucks all the air at the bottom and prevents its neighboring areas to convect. Now it's fighting against some ambient flow that is coming, but still, and those of you who are sharper can see that it starts to rotate. Still it's prevailing, and then at some point you will get this pinhole eye that we identify as hurricanes or typhoon in that case because it's in the Pacific. And this is basically our hurricane or typhoon being born. It is still one of the most difficult to understand majestic processes in atmospheric dynamics. now that you can already see the eye, there will be some kind of an instability process in which a disturbance will travel inward and increase the eye size. It is called an eye wall replacement cycle. And it involves the stability of the structure, that it's slightly less stable at the moment. And you would see it's wiggling a little bit, and at some point it would massively expand. Here, how it's happening. Yeah. And that is a mature typhoon or a hurricane. Okay? So that process we saw now is actually the way to cross down with these red arrows that I showed to create local organization in a turbulent environment. So this is one of the reasons to assume gradient wind balance. Without it, hurricanes wouldn't even exist. So what is a gradient wind balance? So it's basically all of this work that I'm doing starts from being a teaching assistant of Nathan in his dynamic meteorology course. And Nathan has this really compacted way of representing the gradient wind balance that actually made me think about it a bit further. So if this is the radial momentum equation, Newton's law, sum of forces equal acceleration on the radial axis, u is the radial velocity, v is tangential. And what I circled here is the gradient wind balance, the pressure gradient force, the Coriolis, and the centrifugal. The pressure gradient could be written as a geostrophic wind, but it's just notation-wise, it still is the pressure gradient. And if you scale this part, if you divide it by f squared r, you can get this non-dimensional ratio, or we also used it in my PhD, where Rho is v over f. R is basically the non-dimensional velocity squared plus the non-dimensional velocity equals the pressure gradient non-dimensional. And you could plot the left-hand side, r squared plus Rho, on the Rho axis. You get a parabolic shape. We did it in high school. And then ROG would be some kind of a free parameter where you choose what's the value of your pressure gradient. Positive is a low and negative is a high. And you can see that below minus quarter, you don't have any solutions, okay? So if I think of a hurricane as sketched here on the right, at the bottom of the hurricane there is a low. We have a warm core in the middle that flips the pressure gradient or reduces it. So we might move either here or even further down. It's a good question whether we have a high. But if the warm core is warm enough, we'll just throw ourselves outside of the plot. So this would be the gradient non-balance, okay? It's a scenario in which no solution exists for the balance. And therefore, these three forces don't cancel, and some part of the pressure gradient would act on the radial wind, pushing winds outwards, okay? So it's something that doesn't exist if you assume gradient wind balance. So this is gradient non-balance. And if you want to think about it more in terms of physics rather than mathematics, it's the same sketch over again. If you have a low at the bottom of a hurricane, a warm core and a high pressure, and the three forces are in colored arrows, so around the low, the pressure gradient points inwards, the centrifugal and Coriolis will point outward. Both are velocity dependent. If you increase the pressure gradient, you can increase the velocity, speed up your car, for example, to stay in balance, okay? And this goes all the way down to tornadoes, so really high pressure gradients could be balanced. Around the high, on the other hand, the pressure gradient points outwards, the Coriolis inwards, and the centrifugal is always outwards, okay? Now, if you increase the pressure gradient, increasing the velocity wouldn't work because you would increase the centrifugal even more. So there's no solution, okay? So at some point, and that's a question whether it's relevant for hurricanes or not, but at some point you might pop out to the outside of that balance, like what I showed mathematically on the plot. So a bit of a back of the envelope calculations for it. So if we have a hurricane at the tropical latitudes like 20, so F is 5 in the 10 in the minus 5, 1 over second. And let's say the pressure gradient force is very moderate, so it equivalents to geostrophic wind of 5 meters per second around the high here at the top, negative, but very, very moderate. And the radial scale would be 100 kilometers, which is completely reasonable. I will show later that the most frequent radius of a hurricane is 70 kilometers, so 100 is obviously a good number. Then if you punch these numbers, ROG would be -1, which is 4 times below the threshold. -1 is not a lot, but it's a non-dimensional quantity, so it's irrelevant to talk about big or small, just in terms of the threshold. So that's just the ballpark numbers to show that it should exist. And right now what I talked about is how we can create it by heating the warm core and bumping it up, but the picture becomes actually more complex if you move to more 3-dimensional structure. Instead of warming up the warm core to bump the top and be out of balance, between gradient non-balance, you can actually move it around because sometimes wind would push the warm core away from the surface flow. So what I plotted here is it's a bit pixelized, but Basically, in blue contours is the 850 millibar, let's say the lower level low, and in red contours it's the warm core, the vertically integrated temperature, and their sum is shown here, the 150 millibar is shown on the right. It's a very heuristic kind of playing with Gaussians in MATLAB. And what you see that if you take the same warm core, I haven't changed the temperature, but you just slightly offset it, the resulting pressure map will be very strange. You will have this bipolar, like a dipole shape with a high here and a low here. If you put it back inside but make it wider, okay, just making the warm core wider, it's hard to see it in the isobars, but there's a width ratio, you would get this kind of an annulus shape, kind of like a donut. And if you do both offset and making it wider, you will get this horseshoe shape, which is more characteristic to what we actually see in models, and I will show you now also in observations. And the reasons for the offset, as I said, could be a wind that's pushing the warm core away from the surface slope. The difference in widths is expected, if you remember what I explained in the beginning with the angular momentum, that the hurricane flares out. So the lines of air rising are rising in a slantwise manner, so higher parts of the hurricane are expected to be slightly wider than lower parts. So that's why we think that this and these two effects, or they're combined, are relevant. And you can very easily create some kind of a high pressure at the top. I could take, which I will do now, the axisymmetric mean of this shape and calculate whether it is in gradient balance or not. So the ROG at the top of a pressure map might look like something like this. At the center, you would have a low, so you have positive ROG. At some point it becomes negatives. It's really hard to see the graphics, but below below the threshold here. And so you have some amount of imbalance, or non-balance, sorry. And then it like levels out and becomes flat. And so I could calculate this area for each of these plots, and I could sweep the parameters and show a map of the value of this area, how much non-balance you have at the top of the pressure map, how much of a high you have compared to different width ratios and compared to different offsets. And you see that basically when you look at this map, 100 kilometers is already too much because the warm core is outside the hurricane. It's like an exaggeration. Most of the domain, these four stars are actually the 4 cases plotted. Most of the domain is actually out of balance. So it would be actually, based on this argument, it would be actually magical or very surprising to see if hurricanes are in balance. It's more likely that they are not, okay? So this is what we understand from this heuristic model. And it gives some importance to the warm core. Now, the warm core is kind of a debated topic in hurricanes, whether it is important for its intensity or not, and how. Yes?
You're running very fast.
Okay, sorry.
No, just a question. If you don't have the balance, does it mean that turbulence becomes more important?
It's a great question. Would I flip back? I'll flip back, just the equation would help us. Okay. If this vanishes, but still all of these 5 terms balance each other, you still have some kind of a balance. It's just more complex. It's not 2-dimensional, it's a 3-dimensional, like steady state. Okay, so I think this is what it means. It's a good question. And actually I don't know. What I see is that hurricanes still exist with it. So it's not turbulent. But it's a good question.
Why not time dependent?
What?
Why not DUDT?
Well, it could be also time dependent. It could create time changes in the pressure, so you would reduce the surface pressure by doing it. Sorry. Okay. Sorry, maybe I am running fast. I'm not sure of the time. So what I wanted to say in this short intermediate slide is that what I'm saying actually in these slides is that the warm core, its location, its structure are important for hurricane intensity, and this is some kind of a debate topic in the community. So while some papers, as Steve Durden is actually collaborating in this work published in 2013, he showed here the ratio between the height of the warm core anomaly, the maximum anomaly, and the minimum of the sea level pressure, and he showed some relation between it in different observations. Other people has been arguing that the position of the warm core shouldn't matter, because if you project downwards to the surface slope, the fact that the warm core is here or here wouldn't change. It's only its integrated values that would change. And so assuming this top with no pressure gradients doesn't give the warm core a lot of importance. On the other hand, in the National Hurricane Center, they do use the warm core position as an indication of strengthening. This is from Hurricane Igor in 2010. So indicate upper level warm core has strengthened and moved upwards from 300 to 200 millibars, suggesting that I core is likely to strengthen. They do use it operationally as a meteorological indication. Warm core is moving up or moving sideways, and we try to understand something, but the theoretical basis for it is still missing.
Is it moving or expanding? That's difference.
Yeah, it indicated upper level, it's moving up. But
not
that's
an expensive cooling down.
what?
Not an expensive cooling down.
No, the maximum anomaly is moved up. But I think that, look, I think that this is more like a meteorological thumb rule. Something has changed with the warm core and we think something is coming, but there's no theoretical basis to really say what is the scenario which is correct to interpret. And also the correlation here is very, it's not great. And I think a lot of people criticized it, but I think it comes from the fact that just looking at the position of the warm core without looking at the three-dimensional structure, without a theoretical basis, is still missing.
What's the straight line?
I think it's like the feeds that you get and you put it in MATLAB or something. I'm not sure. I didn't publish this paper. It's
No,
still, but
so what does he claim? What does he claim straight line means?
this one,
Yeah.
I think he tries to show the trend of the whole points that he has on the plot, but
It seems like the Miami gunshots.
yeah, yeah. I do think that it's not as simple to just pin the point of the maximum anomaly in the warm core and the strengths of the hurricane. You need to see more like this three-dimensional structure, and I think this is missing both in the plot and in the operational practice that they use. So now we'll go to, in brief few slides, to some numerical simulations of hurricanes in two different models, and show the results there of non-balance and how it correlates with hurricane intensity. And then I would go to observations. So the first model is the weather research and forecasting, the WRF model that's heavily used for hurricanes. And we have 12 simulations of hurricanes in a variety of physical setups. Some hurricanes are actually on the sphere with ambient meteorology, and some are some kind of a flat earth, like what we call the F-planes, they don't move, and without or with some ambient meteorology. Then we go to the North American Mesoscale, which is a Mesoscale weather model that's used in America on a 12-kilometer resolution. Operationally, it's basically based on the WRF model, but reduced in resolution and with some convective parameterization. It is considered less of a research tool, but still the findings we had there are still, I think, striking.
Why don't you give ECMWF?
No, the resolution is too low for ECMWF, I think. I mean, I didn't try, but maybe I could have. The most frequent radius of hurricane is like 70 kilometers, and the ECMWF, they have localized, but maybe only in recent years. Yeah. At the time when I was looking, I mean, this thing with the North American Mesoscale, it started when I was starting my PhD as some kind of a side project that didn't develop, and at the time I think the resolution was 20 kilometers maybe, or something. It seemed a bit poor, but maybe today it's better.
Quarter of a degree is probably.
What?
Maximum probably a quarter of a degree.
I think, yeah, it was a quarter degree at the
But they
time.
were the most successful in forecasting the trend.
So in the recent years, since Sandy, I think, or something, it's in 2012, they increased the resolution locally and started providing hurricane forecasts, and they were the most successful in Sandy. All the models threw Sandy back to the ocean and then waited inside. And also recently in Irma, they had a better forecast than anyone else. So at the time, it seems like not a good choice, but today it might have been, or be doing something else, but it would be interesting to check. So in the WRF simulation, let's start with the F-plane. It's a very idealized scenario where the hurricane is not moving, it's just sitting up. And what I show in this multi-axis plot is in black the maximum velocity, in blue the radius of maximum wind, the radius in which you meet the maximum velocity in kilometers, and in red this integrated non-balance that I illustrated before, the total area non-balance. Over here you see the 150 millibar pressure maps or geopotential and height map in 18 hours, 32 hours, and 120 hours. And you can already see that you start with some localized high that extends to something very big and drastic and then tapers off completely. So you don't have a high. And you can also see it here in this time plot. So what you see here is that the hurricane starts like a very wide and very weak storm. It shrinks and intensifies at the same time, again due to this angular momentum conservation, like a ballerina shrinking her hand and rotating fast. So it shrinks and it spins up. At that point you have a peak of non-balance, and then it vanishes completely. So based on this model, you could assume that the final form of a hurricane is in gradient wind balance. Actually, maybe the process was involved with some deviations, but at the end, you're some fixed balance. When you look out of the F-plane on a realistic sphere with meteorology, and you do the same trick, so you see the pressure max here again in the same plot, you see that the hurricane starts wide and weak, and it shrinks and intensifies, but this non-balance actually prevails throughout the simulation. So the hurricane on the sphere does not obtain this balance, and so maybe this key component, especially in the intensification phase, when the velocity increase, is important. So what we did is we looked at the difference in the velocity from the minimum to the maximum, okay, throughout the life of a hurricane, and at the area under this plot, and we correlated the two, okay? How much of this existed in the simulation. So these are the 12 hurricanes. We have one outlier that I don't know to explain honestly. But apart from this one outlier, we have quite a trend between 12 simulations in completely different physical setups and all in the WRF model, between the intensity change in the hurricane through its lifetime and the entire amount of non-balance that occurred in the simulation. Our co-authors suggested taking the 24-hour values because 24 hours are an indicator of rapid intensification. That's the period of intensification. So what we did in this plot is each gray dot represents the value of 24-hour mean of this non-balance and the 24-hour mean of the maximum wind, okay, each gray dot. And each large dot represents the peak non-balance per storm and the corresponding velocity it had at the time. So what you see that basically there is a correlation between the highest point of non-balance and the velocity at that point. So it's trying to say that maybe the maximum velocity of the hurricane was not at the time of maximum non-balance. But if you take its maximum non-balance, you would see that between different storms, as this maximum rises, the intensity at that point is higher. So it is important for the intensification, even though the final intensity might be unrelated. So that's what we see from this plot. It's a bit of a trickier message. And we published it recently in GRL. And then I would move to the North American Mesoscale. This is the results we...
Do you have the same correlation also with heat flux? With the vertical heat flux?
No, I didn't check, sorry. With the vertical heat flux? Like the convective activity? No, I didn't check, I don't know. It's a good question. If I have the correlation with the vertical heat flux. I would guess that the heat flux would be proportional to the wind at the surface, because the stronger the wind, the stronger the heat flux, and the convection just have to carry it up. It has to. It cannot just keep it, like the minute you have flux of heat at the surface, in terms of latent heat, it would convect upward. So I would guess it would correlate, but I didn't perform it. I will go now briefly in the North American Mesoscale model, the other model. What I did here is I plot only the sizes of hurricanes, okay? So it's a probability density function of hurricane sizes. In the North American Mesoscale, we had a much bigger population of storms, 53, 741 pressure maps. And so from each pressure map individually, we looked what is the size of the hurricane, what is its winds, and whether or not it had non-balance at the top. So it goes slowly. First on the gray line. The gray line comes from a large data set of hurricanes that has only size and intensity and time. So I cannot calculate non-balance for it. And it's for 11,480 pressure maps. So it's a huge data set. It's called the Extended Best Track. It's maintained by somebody in Sirius in Colorado. And if you do the probability density of hurricane sizes on that huge population, you see that the most frequent one is roughly like 60, 70 kilometer radius of maximum wind. That's the most common size for a hurricane. And you see also the huge variability. Now if I go to our model, where we have not only the size of the hurricane, but also complete pressure and wind maps, and we calculate if there was or was not non-balance. So the entire population is here in the black line, and you see this bimodal distribution. And if I split it into with and without non-balance, which is the blue and the red line, you see that the part with non-balance explains better this peak of sizes, whereas the other peak is better explained by those without, okay? So it seems like in this model at least, there are two populations of hurricane. One in which there is non-balance at the top, they're maintained with a different steady state or quasi-steady state, and one in which there is a gradient mean balance throughout the hurricane, like that older theory I showed before, and where the steady state is different, and the size is different. I'll just remind you that this ROG, the non-dimensional parameter that I'm looking at, it is inverse proportional to the radius, so it is reasonable that smaller hurricanes would have an easier life breaking this balance, reducing this below minus quarter, whereas larger hurricanes would be harder. And if you remember the back of the envelope calculation I did, my radius was like 100 kilometers, so it all sits here somewhere in the middle. And if you take these, only the blue hurricanes, only the population of hurricanes in which there was no non-balance at the top, and you correlate, again, the intensity of this over the hurricane on average, and the average of the maximum wind for the hurricane lifetime, you see again that the two correlate. So at least in this one population of hurricanes, it seems that non-balance and intensity play together. I cannot infer on causation, of course, causality is not coming from correlation, to say whether non-balance is a result of the hurricane intensity or it causes hurricane intensity is a much harder work, but at least we see that it correlates. I'll just point out that out of 741 pressure maps or 53 hurricanes, in this group, 28 are part of it. So it's not like a small fraction of the number of hurricanes I checked in the simulation, it's roughly half of them. Okay, it's not like I'm taking 2 out of 50 and say, oh look, there's a new phenomena. It's actually part of it. Now, what is the time? Yeah. What is, no, I can see, my eyes are like
10-40 minutes.
10:40, 10 minutes?
No, 10:40.
10:40? So how much do I have? 10 minutes? What? No, 10 is enough, okay. So now we'll talk about observations. It's really like a couple of slides and we're done. So flight observations. People actually fly through hurricanes. I don't know if you know it or not. It's apparently it's not as dangerous as people thought. Flying through a hurricane is actually started, like many other good things in history, started by somebody getting drunk. So this guy, Joseph Duckworth, was like a very famous flight instructor in the American military in World War II. And it was just the time when they started what they call it, I think, instrumental flight, right? Something like that. Just when the time this started. And he had some British correspondents in his military base, and they went to drink together, and he was like cocky, and he was like making a bet, I can fly through a hurricane. And they said, no way, you can't. And the next day in the morning, he got up, he took one of the airplanes, and he flew through a hurricane. The guys in the meteorology in the base were like flying, like they were freaking out to hear about it. It was like, you have to take us, we want to see what's going on there. Later on, they started taking measurements. Now there is a flight unit of NOAA or of the National Hurricane Center called Hurricane Hunters, and they fly through hurricanes and take measurements routinely. Every hurricane that goes to the US, near the US, is having like 3 or 4 flights a day. And there's ample evidences of measurements from hurricanes. This is from a very old paper from Hogg Willoughby from the 90s, where they report 900 flights through hurricanes in lower levels. Okay, these are flights in the 850 millibar. And what you see, it's kind of, they fly something like this, like transects, and they take the measurements. What you see here in the solid line, in the dots, is the measured wind. What you see in the solid line is the wind you would calculate from the measured pressure, assuming gradient wind balance. So at that level, the gradient balance is flawless, okay? It's a perfect assumption. Sadly enough, there's not a lot of flights flying high above hurricanes. These airplanes that they're using, the Ivy Gulfstream, and I don't remember the name of the other airplane, they're limited by flight level to 8 and 10 or 12 kilometers. And the 150 hectopascal, where I predict my non-balance, is roughly 15 kilometers high. Okay, so there's not a lot of measurements. And I would just remind you that in order to measure non-balance, because there is no balance between wind and pressure, you cannot measure the wind, you have to measure the pressure. Winds are easily measured by satellites, by moving clouds and tracking them. Now, after a year in JPL, I've spoken with a lot of people, and it's very easily done. But measuring the pressure, you have to locally have a device which is what they typically do is they throw with these things called drop zones through the hurricane that transmit the pressure and their location, GPS location. It so happened to be that as I was sitting here in the Hebrew University and thinking about hurricanes without even knowing people in the community, the American Navy has issued a huge campaign, and it's really by chance. I flew to a tropical meteorology conference and heard about it, and I was like, I couldn't believe my luck. They issued a huge observation campaign in 2015 to measure the hurricane outflow. It's called Tropical Cyclone Intensity Campaign, or TCI, and they use the WB-57. It's a maximum flight. It's an espionage or a reconnaissance airplane by NASA, where they put the National Hurricane Center devices and threw them through the hurricane at roughly 18 kilometers. So the flight, like the airplane flies above the hurricane in some kind, they call it a figure 4 shape, okay? And it throws drop zones actually in quite an impressive density in this campaign through it. And then they get the data. And on April 1st, 2017, this data was available to the public. They had an embargo on the data for the first year to publish on their own, so they could write their box paper. And this year in April, it became available to the public. And I was like sitting in lunch in JPL in NASA, and I spoke with this guy named Steve Durden, the guy who published this line that he didn't like. And I told him this, and I had this idea about the outflow, and there's new data, and I'm thinking about working on it, and he got hooked, and he said, listen, I don't have a lot of time on my project, I'm flying to Africa to some campaign, but let's do the weekend thing, like, we can meet once in a while and email and work on it. And so we started analyzing it. So first what I did is, we analyzed it in 2 ways, and it's really like, when you analyze data, you have to be very careful. It's so sensitive to, like, interpolations and parameters, and I'm calculating gradients of the interpolated data, so I'm very careful to try and prove first myself, but then everyone else, if I see what I see is true. So if we had this airplane trajectory here, one thing I did was to take 1, 2, 3, and 4 cross sections as they are, scale them on the radius of maximum wind. So if I'm not exactly in the center, if the hurricane is not circular, I'm stretching them, and they take the mean. The assumption behind it is that the hurricane is roughly axisymmetric, so that the mean of these 4 would represent the structure of the hurricane. Steve came up with this paper that he so recently published of a 3-dimensional interpolation that based on wave number composition. I'll show both of them, and then I will conclude. So that 4-section mean, this is from Hurricane Joaquin 2015, from the campaign, in gray shading, this is the mean, it's a radius, in units of radius of maximum wind, so 1 is here, and the pressure, the vertical axis. The gray shading is the velocity of the hurricane in meters per second, up to 40 meters per second in the measurement. The red contours that turn into blue is the temperature anomaly from its horizontal mean. So what's the difference between this mean, in Celsius or Kelvin, doesn't matter, it's an anomaly. So you see the warm core here sitting between 300 and 200 millibar. You see some cooling at the surface here near the maximum wind, and that's because the winds are evaporating from the surface. And in theory, the ocean is constant temperature, but in practice, there is still like cooling from this evaporation. And we see in purple contours this non-balance higher up, above the radius maximum wind, around where the models predicted, okay? Around the same scale, it's roughly 100 kilometer distance. You see this non-balance sticking out to values of minus 90, okay?
It is adiabatic cooling to some extent.
Adiabatic cooling?
Yes. Because the pressure drops 100 millibar almost.
Okay, it's a good point. Anyway, in theory, we assume we have a warm core here, but a constant temperature here, but I meant to say...
Potential temperature is rising still.
Yeah, of course. Yeah, the potential temperature is still rising, it's true. And so here at the top, we find this bulb of non-balance that slightly resembles the models. And then in the wave number decomposition, so it's a paper, really recent paper that I think he might have reviewed or something, but he just said, listen, it's a great timing, I just read this paper, I was wanting to try this method. The idea is that if you have what they call a wind speed field, okay, they took a WRF model, subsample it, and play with it to show how you can compose. So this is the true data, these are the different compositions of this data. Based on the methods, it says that the model data is composed out of sinus and cosine functions in the angular, and you just decompose it and build it with some radial-dependent coefficients that you build from this integration. Not really interesting, but this is like the 0, 1 wave numbers. You add a second wave number, you get more features, you get the third, you get more features, and eventually you get closer to the original field.
So 1, 0 to 3 almost
Yeah, that's the main point of the paper. Even 0 to 1 is very impressive. They try to show it by reconstructing the maximum point of wind, because that's what people at the surface care about, is where is it, right? So they showed it and they said basically 1 or 2 wave numbers is enough to get the maximum wind correctly, like that. The peak here and the peak here. It's quite an impressive method. And now I'm going to show its result from what I'm doing. Now it's recent and I'm still playing with it, and I have to say this interpolation is resolution dependent, how you choose to interpolate, and I'm still trying to make it more and more robust, but it's actually something I did on the flight. So this map is like similar to what I showed you before. It's 850 millibar in blue and the mean temperature in red. So you see where the warm core sits compared to the low. Okay, it's slightly offset. Okay, the temperature anomaly is slightly offset in the horizontal plane. And this is the upper pressure map that you get, the 120 millibar level, the 15 kilometer, from that decomposition. And the white dots are the drop zones involved in this decomposition. Okay, so you see all the white dots. These are the actual data. So it's quite impressive. And you do see this shape here, this high pressure anomaly, quite similar to the Gaussian model, the MATLAB game I showed you before. This is the non-balance calculation at edge points. So you get like up to minus 35, okay? And you see it peaks exactly where the pressure is. And then I was able to compose it to some kind of three-dimensional picture, okay, this data. So what you see here, the vertical axis, is the potential height. Here it's for the 150 millibar, here it's for the 850 millibar and 120 millibar. At the lower levels you get a low, okay, as we know. The 180 millibar is projected here in blue, and next to it is the mean temperature. So you see a warm core that's slightly offset from it. And at the top you see this dipole shape with a low and a high around it. And the color is really hard to see, but this is the non-balance, is the red part, is where balance vanishes. It's negative values up to minus 50. And the drop zones are shown here, so that's the actual data. It is magical / I still doubt if you can get so much information from so little data. It is impressive, but I still suspect it. It's not something I'm writing right now or anything. But the only thing I can show to justify it or to support it is a similar figure from a model. Okay? In the model, we do have the three-dimensional field and not just the sum sample one. So this is from the North American Mesoscale model. It's another hurricane completely from 2010. You have a low at the bottom, you have a high at the top with a very strange, this time more of a horseshoe shape. The warm core and the low are slightly more aligned than here. And that's why you get more of this axisymmetric shape. And again, in red, you see these values of non-balance that slightly correlate with the isobars at that level and also divergence of the wind. So this is basically, I get the bottom point. I would conclude it with a cartoon rather than a list. The original model, if you remember, had a straight line here. And basically, what we're trying to suggest is that maybe this circle that connects how we understand hurricanes, we need to add like 2 more stages here. So instead of a warm core projecting directly to a surface low when the top pressure is flat, we think we might need to add another mechanism, a very strange shape high, non-balance that might lead to divergence because the radial pressure gradient would now act on the wind, actually pushing it outwards. Divergence in turn would give you a lower pressure at the surface because you remove mass overhead, and then wind, surface fluxes, convection, warm core, and so forth. This is the conclusion of this work. I would leave you with a photo, a picture that reminds us how important it is to understand hurricanes. This is again from Hurricane Harvey. I hope you don't know this place or your friends don't live here, but
It was not Hurricane Harvey that flooded Houston. It was convective bands that occurred maybe after the hurricane died.
No, it stayed there, it lingered.
No, it was not that.
what happened, I recently heard, we had a talk by Kerry Manuel just about it. I think what's so strange about Hurricane Harvey wasn't its actual existence. It's a case where, for us, of course, it jumped by surprise because it intensified quickly, but the fact that it was blocked by other meteorological phenomena to sit roughly around the same area for 24 hours and raining a lot, whereas if it would just pass by, things would be...
It was not the hurricane, okay. I'll schedule the seminar and I'll show you.
Yeah, okay, I'm not arguing. Okay, thank you. Danny? Yeah.
First, I want to dispel the general belief that Hurricane Harvey flooded Houston. It did not.
Okay, I agree.
It went over Corpus Christi and died inland, and then convective rain bands that were extremely juicy and powerful kept coming flowing in with lots of thunder in Houston area.
You do not consider convective rain bands to be part of the hurricane?
Not after it died.
It died, moved on to Louisiana.
Okay. It's definitely not the topic of my talk, and I'm not arguing. Okay. Yeah. Okay, but you had a question.
It is essential. It is.
Yeah.
It is something. It's a misconception that is misleading many good people. That has to be dispelled. That phenomenon instead has to be understood to really get to address the problem right. But the question. The whole existence of a hurricane is a hurricane could not, or any warm low could not exist if it was just pure gradient balance, because there would be no cross isobaric flow.
It's true.
At the low level, you balance it with the friction, surface friction. But at the upper level, that is where without imbalance you cannot maintain or enhance the.
So the current theory of hurricane says that at outer levels the air have to go out only because it went in below.
Yeah,
it goes in below because of friction, and then what would you do? You have to conserve mass. So if it goes in lower, it has to go out.
How you satisfy the equation of motions? That's the point.
You satisfy it because you bring angular momentum from the bottom. You have a flux of angular momentum that causes it to flare out. I think it might be enhanced also by a pressure field, but the pressure is considered. I really mean the opportunity to sit like people like Kerry Mano, like the leading figures in studying hurricanes, on a one-on-one conversation. He's really nice and he was listening and he told me, listen, generally I think of pressure as a non-interesting variable. For me, it's diagnostic. Once you have balance, all you need is the winds. So people think that once you obtain your balance, pressure is out of the picture and you have to solve only the winds. What I'm showing here is that the balance doesn't exist. You have to think of pressure as an interesting variable, which is more talking to professional meteorologists who look at pressure maps. So I agree with you, but I'm saying the current theory is not flawed in terms of the equation of motion, but it just says that the upper level is kind of just a passive component that reacts to what happened lower. You bring the air in the bottom, you have to get it out at the top. That's the current theory.
The expansion is not enough. It cannot explain intensification.
I think so as well. Yeah, I think so as well.
You need some source of convection from below.
Sorry?
You need some source of convection from below. It won't work otherwise. Hurricane will not be sustained simply because you started blowing it clockwise or counterclockwise.
Yes.
You need some sort of convection from the lower level of the atmosphere.
Exactly, but when you bring this convection and you create heat, the question is, does it just project downward to get a low, or does it create a very strange circulation pattern that reduces the pressure? Or if you like, you asked what I remember when I was your teaching assistant, we had this question for students. If you warm the temperature by 2 degrees, what would be the pressure at the bottom of the ocean? It would be the same, right? Saying that you can take temperature and project it into the surface in the bottom is a wrong argument, because it's only the overhead mass that gives you the pressure, not the temperature. Temperature is how well it's distributed. So the idea that you can take temperature and project it to have the bottom pressure, I think, is a bit crude and we need to rethink it, but I agree with you. Or, Nathan?
In your basic model, what you have is two dynamical components that could contribute, I would say, to the, I don't know what you call it, non-balance, it's the imbalance.
So imbalance, terminology we can talk later, okay.
I'm not sure why you call it, but why not simply
There
imbalance?
is the reason, yeah, okay.
I'm sure there is, because hyphen is not a good term. But anyhow, what you have is both the temperature, say between 850 and I don't know what,
150.
150, that is offset in terms of the center from the low level.
Low, yeah.
Low. And so that is plausible. It doesn't have to be right on top of it, it can shift a little bit. But the widening is something that we also have another second, which is the
widening.
Width, or in your case, both were Gaussians, right?
Yeah, both were Gaussians for the idealized.
But the width somehow changes. Now, why would it widen? Why would the temperature distribution in the layer be so much wider?
Actually, in the introduction, maybe I should have pointed it out better here. When I said that the air has to flare outward because of angular momentum conservation, the two conserved quantities at the top of the boundary layer are angular momentum and potential temperature, equivalent to the moist, like theta E or moist entropy. And so these are lines of angular momentum and moist entropy, and they flare out together. So what you have is the same value of moist entropy here, you meet it outward here. So the warm core is essentially wider than the surface low. It is essentially wider in practice. That's the reason. It's because the same air conserves both angular momentum and theta, but it has to go outwards because of the angular momentum consideration.
So you slowed it down somehow.
The velocity slows down, of course, yeah.
Why?
Yeah. You have some pressure gradient
so
here.
Why did you slow it down?
You have some pressure gradient here. As you go up, the pressure gradient decays because of the temperature. So it slows down. It still is in gradient balance. So V prime is smaller than V, therefore R prime is larger
so it
than
slows
R.
down because of the pressure.
Yeah,
and
because the pressure
increases.
Yeah. 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 Ori?
Nice. I think we're out of time.
Okay. You can one.
Your observations, the most recent part of the latest part of the talk, essentially suggests that the non-gradient terms were W times du dz plus U times du dr, and so it seems from your observations that really the non-gradient balance term is the du dr term, where you have the zonal wind maximum. The change in zonal wind is so strong that this term just cannot be neglected. That's basically what you're saying. The peak in the non-gradient balance in the horseshoe essentially around is a little bit off the radius of maximum wind, right?
Yeah.
That's basically what your observations are showing, but the equations are also sort of predicting that where you have a really strong change in zonal wind, the UDR is very large. That's where you're getting the gradient non-balance.
Yeah, the UDR, you think about it as a change, it's also in the axisymmetric thinking, the UDR is the divergence also. It's not only the advection. It's roughly the 1 over R plus the UDR would be the divergence. That's where you get the divergence, it's true.
So that's really, that's the consistency here. It's not the W times the U d0, right? So it's the other term. It's basically essentially where the change in zonal wind is so strong that this term is just not negligible anymore.
I think maybe to cast to everyone the question in a better term, what you're asking me is how to interpret non-balance, while I was focusing this work only in proving it exists. Now, I have to say it's really hard when you talk to people who are not from the hurricane community, tell them there's no balance at the top of hurricanes, they say, so what? And you tell it to people from hurricane communities, they say, no way. That's basically. So what Ori is talking about is these two terms. So I was...
He's talking about three.
Sorry? Yes, 3 terms, of course. I don't even know if it's time-dependent yet. What I was talking is calculating this one to see if this balance exists. What you're talking is how to interpret it in terms of the flow. It's a big question. I have no idea how the flow looks like when you don't have balance. Like, how can I simply characterize the flow when you don't have balance? It's something I'm thinking about a lot. How can I show a simple model, not a full 3-dimensional numerical model, but a simple model that tells you this is the flow without balance, this is the flow with balance.
And assume there is such an explanation, maybe there is not.
Maybe there isn't. No, I'm just saying. So what Ori is talking about is how to interpret the non-balance here in terms of what happens to the radial velocity and acceleration here. And that's something that's definitely ahead of me. I don't have a clear answer now.
Is the flow turbulent up there?
So, 101, everybody need to go, students and stuff. Basically, in the upper level of the atmosphere, you have static stability. The atmosphere is more stable. And this is a sink on turbulent kinetic energy. Now, unlike in turbulence, what I'm working now is convection and turbulence. I'm learning it a lot. I'm trying to solve this convection. And exactly in the upper level of the atmosphere, the atmosphere reduces turbulence all the time while generating it in lower levels in the boundary layer. So it shouldn't be too turbulent, but there is convection, so something would be there. It's a good question, what's the measure of turbulence in that?
Not exactly.
Potential participants is not sure.
Sorry?
Not exactly.
Let's continue.
Okay, yeah. I think we have a lot of conversations going on. Thank you.
הנקודה היא,
כן, דני.
הנקודה היא שבשביל לחפש את האנלוג לסיטואשן בגאונד אלקטרון, התפתחות האנלוג לשום, ושם הייתי מצפה למרות שאתה בבלנס, אתה חייב לתת טורבולנציה עם פלוק שניקח את זאת הייתה.
תודה.